All right, so it is 3:30. We can go ahead and get started. All right, cool. So just a little bit of housekeeping before we kick off. So homework assignment 3, that is due, sorry, not tonight, tomorrow night. So again, if you have any questions about that, I do have my Friday office hours as always. And yeah, so we did go through our first round of checking Tuesday on Tuesday. So it looks like for the most part, everybody did well on that. And so again, the main way that you can mess up the checking Tuesday is, if there's some sort of like technical issue, you don't meet all the specifications, like you forgot to turn your camera on or something like that. Or you're given this question and then you really just have no way of explaining your thought process for it. And so again, if you get the full amount of points for the checking Tuesday, that doesn't necessarily mean that you got it right, but just more that you were able to articulate your thought process. So what I'd like to do is also just kind of give some suggestions and pointers about any misconceptions that you might have kind of exhibited in that discussion. So I'd like to give those pointers in I guess like the Canvas comment section. So do make sure that you're kind of looking at that feedback just to make sure that you do have the correct understanding, if you will. So hopefully you find this as a useful way to get feedback as well. All right, and so what we're going to do today is finish up with this Unit 4 in which we talk about or give a brief overview as to how the TSNE algorithm works. And then we're going to talk about essentially how we can use the resulting TSNE plots with carefully selected parameters to learn more about some aspects of the clustering structure of high-dimensional data sets. And again, you want to remember the TSNE algorithm is not a clustering algorithm in and of itself, but it is a dimensionality reduction algorithm, which we essentially use as a very helpful, insightful aid in our cluster analyses, in which we use actual clustering algorithms. So that's our plan for today. So yeah, any questions before we get started? Okay, great. And so just as a quick recap, there are things that the TSNE plot can and cannot suggest to us about a given data set. So we've discussed some of the cool things that it can, in fact, suggest if we are interpreting them correctly. So we talked about it can suggest information about the clustering structure. It can suggest information about the shapes, the number of clusters, the number of observations in each cluster, whether or not those clusters are separated. And in addition, it can also suggest information about how a set of pre-assigned class labels associate with this identified clustering structure. And it can give us suggestions about how a set of, for instance, cluster labels might associate with this suggested clustering structure from the TSNE plot. And so, like we discussed, the key parameter that you need to be very careful about selecting is this perplexity parameter that we discussed. And again, the perplexity parameter represents how many nearby neighbors we are assuming each point in the original data set has. Because basically the way that the TSNE algorithm works is it forces however many neighbors that you think, or however many neighbors the perplexity value is stipulating. Basically, for instance, if our perplexity is 5, what that does is it finds roughly the 5 nearest neighbors of a given observation in the original data set, and it forces them to be close to those corresponding nearest neighbor points in the TSNE plot coordinates. Okay, so we discussed that there are some aspects of the original data set that the TSNE plot will not faithfully represent. So for instance, one of those aspects of the original data set are the outliers. So basically all outliers, provided you're selecting a perplexity value that is larger than 1, will in fact be forced to be next to its nearest neighbors in the TSNE plot projection. There's actually other things that a TSNE plot will also not preserve. So we'll talk about what that is later on in the unit. And again, so we're getting into the main idea as to how the algorithm works. So basically, like we said, we're setting up this optimization problem that seeks to find the optimal two-dimensional TSNE coordinates in the plot that we're looking for that minimizes the distance between two similarity matrices. So P is our specially designed similarity matrix between all points in the original data set, and Q is our specially designed similarity matrix between all points in the two-dimensional projected coordinates. So just as a quick recap, we're very careful about how we design this similarity matrix for P. And what we end up using is basically a normalized Gaussian curve for determining these similarity values between two observations in the data set. So for instance, what we end up using, and we could use, so basically we do end up using, for instance, most often the Euclidean distance to create the final similarity matrix, right? Because basically if we wanted to come up with the similarity values between, let's just say, observation 1 and all the other observations in the data set, what we do is first, we create essentially a function of a Gaussian curve with a specially designed standard deviation value for that particular observation, in which the distance that each of those other observations are from the observation that we're considering, so x1, is basically plotted on the x-axis. And then basically how high on the Gaussian curve that corresponding distance is dictates the similarity of those, let's say a given point x2 to the centered point of x1. And then basically we perform this normalization in the denominator for this, this numerator value that we're creating here. And then also there's this sub-optimization problem that's actually performed as a pre-processing step that carefully selects the right standard deviation value for each observation such that the number of observations, let's just say for, this row here that corresponds to observation 1, such that the number of observations that have high similarity values, i.e. those that are considered close or similar to observation 1, is going to match roughly the perplexity number that we've specified. So for instance, if we've specified a perplexity value of 2, then what this means is that for each observation in the data set, what the optimization problem is encouraged to do is give high similar values to the two nearest neighbors of that particular point, let's just say, and then give low corresponding distance or similarity values for all other points in the data set, essentially. So it might be, so for instance, object 1000, its two nearest neighbors might be 1 and 2. So it might do something like this, so on and so forth. So we'll talk more about the nitty-gritty of the mathematical equations as we basically wrap up the course, because what we essentially want to focus on first and foremost is how to go about correctly interpreting the results of our TSNE algorithm in order to aid or effectively aid our remaining clustering algorithms that we'll talk about in the class. So that's how you create the similarity matrix for the high dimensional or original data set observations. Now, the way that we go about creating our other similarity matrix for our two-dimensional TSNE plot coordinates, which are not actual points themselves, but they're actually decision variable points that we're solving for, is going to use a similar function, if you will. But rather than using a normalized function of a Gaussian curve, Maybe you've seen this function before. What we are instead going to be using is a normalized version of a t-distribution PDF curve. So you want to remember in the t-distribution, there's no standard deviation parameter that we flexibly or that we can adapt. It's simply the spread of the t-distribution is dictated by the degrees of freedom. So in particular, this function that we're going to be using here to calculate the similarity of the projected coordinates is specifically going to be using degrees of freedom equals 1. So basically the t-distribution with the fattest tails. So basically there's no parameter tuning involved when creating the Q similarity matrix. It's simply just one curve that's considered for all points. But basically we use this curve, this function of the t-distribution, to also calculate the similarity between two y coordinates as well, basically. So what we end up doing is, we find again the distance between a given observation y0, or excuse me, a given observation y1 and y2, for instance. And however high up on the curve that distance is, basically that dictates the similarity observation 1 and observation 2 have to each other in the projected coordinates. And then we also perform a normalization step for each of these observations. So that's basically the way that we come up with the similarity matrix for the decision variables. And so someone's asking, so would that mean that the similarity matrix should be symmetric? So this additional step that we take here when creating the similarity matrix for the original data set does in fact force the similarity matrix to be symmetric here. So basically there's a lot of steps in the creation of this similarity matrix, and we'll dig more into this like I said, at the end of the semester. But this is the rough idea as to how the algorithm creates these two matrices. And again, what you want to remember is that this matrix, this Q matrix that we're creating here, this is not actually not an actual matrix of values, but more so it's a matrix that is a function of decision variable values, if you will. Okay. And so once we have that P matrix and that Q similarity matrix, what we are ultimately trying to do, again, like I mentioned, is solve for the optimal value of these decision variables that minimize the distance between the P and the Q matrix. And now specifically, we'll talk more about this at the end of the semester as well. We specifically end up using the KL divergence to measure the distance between this P and this Q matrix, because essentially what we are creating in this P, or in these P and Q matrices, are probability distributions. So the KL, or Kullback-Leibler divergence, what this essentially allows for us to do is to more effectively calculate and measure the distance between multiple probability distributions, essentially. So this is ultimately what we're trying to do. We're trying to solve this optimization problem. However, there's not a fast, polynomial time algorithm which will, find the global minimum to this optimization problem. So therefore, what we do, as we do with many of our algorithms which are based on, some sort of optimization problem, is we use some sort of a heuristic algorithm, which will hopefully find, at the very least, a local minimum to the corresponding optimization problem. So what we do, as we do with, many optimization problems, is we use a gradient descent algorithm. And usually in these gradient descent algorithms, like we saw with k-means, we start with a random initialization of what those decision variables should be in the beginning. So because of that, the TSNE algorithm is a non-deterministic algorithm. Okay. What the algorithm will pursue is a local minimum to this optimization problem here, but sometimes you might be running the algorithm for a certain number of iterations and it's still not converging. So it's always a good idea to stipulate a maximum number of iterations until the heuristic algorithm simply just stops and returns the best solution that it has found so far. And now technically, when we stipulate a gradient descent algorithm, there's always a set of learning rate parameters that are needed. So basically, how large of a step size should we take in the direction of the gradient that we have calculated? So these are parameters that you can technically select in the TSNE function in Python, but they tend to not necessarily be as needed. It's not necessarily the most parameter to focus on, but it is something that you can stipulate and specify as well. But yeah, before we kind of get into the interpretation element of the algorithm, I wanted to just give a quick overview again as to what this algorithm actually does. So the cool thing about the TSNE algorithm it basically, based on the perplexity value that you're choosing, it has this data structure assumption where it seeks to map nearby points in the high dimensional data set to nearby points in the low dimensional data set. So this is what we mean by preserving the local structure of observations. And in addition, the way that it's designed also seeks to map far away points in the high dimensional data set to far away points in the low dimensional data set. So this is what we mean by global structure preservation. But the key thing that you want to, practically speaking, keep in mind here is that especially when you are dealing with lower perplexity values, the TSNE algorithm tends to be better at this aspect. Especially when the perplexity is low. So what that means is that the algorithm tends to be a lot more effective at mapping what are considered to be nearby points in the original data set to be nearby points in the low dimensional data set. On the other hand, if 2 points are far away from each other in the high dimensional data set, they're not necessarily guaranteed to be super far away from each other in the low dimensional data set. They probably won't be the closest points, if you will. If they're not considered to be neighbors, they probably won't be the closest points. But, it is possible that you might have these 2 points that are very far away, that are not neighbors, but the TSNE algorithm, because it's not focusing on preserving the far away distance as much, is that it might actually put them somewhat close to each other, especially if your perplexity values are less. We'll look at some examples of that in just a second. But any questions on that? Okay. In addition, you want to remember, like we've seen this before, the TSNE algorithm has this cool mechanism in which it adapts to the underlying data set. So in particular, for instance, the sparsity of observations within clusters of different sparsities. So like we said, each observation in the data set can have a different standard deviation, which ensures that each point is considered to have a number of nearby neighbors that is equal to the perplexity value. Okay. We want to remember that it also uses a non-deterministic heuristic algorithm to find the structure within the data. But something that you do want to keep in mind is, for instance, we had to create a similarity matrix in the beginning for each of our observations in the data set. So what that means is, or what that translates to, is that this tends to be an algorithm that is much less efficient than algorithms such as k-means. And part of this is because the computational complexity of the algorithm is in an order of the number of observations in the data set squared. We essentially had to create that similarity matrix in the beginning, which means, practically speaking, this algorithm does not tend to be the most effective when you are trying to learn about the hidden clustering structure for data sets that have more than 10,000 observations. Okay, but can we think of a potential workaround for this? Any ideas as to what we could do? So let's just say we want to, you know, determine the clustering structure of a data set with like a million observations. So yeah, exactly. So that's something that we can in fact do here. So we can simply just try taking a random sample from larger data sets. And what we often see is that the clustering structure, the random sample, tends to reflect the clustering structure of the full data set. Okay. All right, so those are just some bullet points I wanted you to keep in mind as we are going through some examples of us using the TSNE algorithm on a variety of different data sets. But any questions on that? Okay. All right, so let's go through a couple examples of how we might use the TSNE algorithm. So what I'd like to do first, actually, is I'm going to bounce to the application. Just kind of show you how we actually create a TSNE plot in Python first. So this is a scikit-learn function. So we use the TSNE function here. And again, we're going to be using this shill bidding data set. This data set that represents various numerical attributes of eBay auctions. And you want to remember that we only want to cluster just the numerical attributes, or we only want to learn about the clustering structure of just the numerical attributes. So therefore, we only want to put the numerical attributes into our TSNE algorithm. Okay, so we do want to drop this class label first. Now, another thing that we're exploring in our current homework assignment is whether or not you might want to scale your data set first. So, essentially what we're seeing is many of the clustering algorithms or dimensionality reduction algorithms that we're going to talk about in this class have this property in which columns, with higher scales will end up dominating the results of said clustering algorithms or dimensionality reduction algorithms. So if you don't want that to be the case, then what you can do before using any of these algorithms is scale your variables. So for instance, I can use the describe function, before performing any TSNE plot projections. And for instance, I can see that, the change in the scale for these, two of these variables here is somewhat different. But for instance, I might deem that, this starting price average scale is not too dramatically higher than this bidding ratio scale. And in addition, you also want to consider that the way that these variables are designed, as we can see here, are basically designed to be between 0 and 1. So we might determine that, this data set does in fact not need scaling because these variables are essentially meant to represent the same, the same units, if you will. So whether or not you choose to scale, that's kind of up to you because you might get different results. But the thing here is if you do plan to scale, you want to make sure that you are scaling that data set before you put it into your TSNE plot as well as your clustering algorithm. So basically, you want to make sure that you have an apples to apples comparison of the data set that you're exploring with these multiple algorithms. Because again, the scale of the data set will in fact, determine the clustering structure that you end up seeing, not just in your clustering algorithms, but also your TSNE plots as well. So we've decided that we don't want to scale based on the fact that we're kind of dealing with variables with the same unit. So we won't do that in this particular analysis. So let's just start with an initial naive analysis of the data set. So we're simply not going to think too much about our parameters like the perplexity value. So I'll just select a perplexity value of 5. And because I'd like a two-dimensional scatter plot, I'm simply just going to specify that I want to have 2 attributes in my resulting TSNE coordinates. And because this is a non-deterministic algorithm, it behooves me to fix a random state for reproducibility reasons. Okay. Now, essentially, because I haven't run any function yet that has the word fit in it, essentially all I've really done here is I've simply just set up the parameters that I would like to use in the TSNE algorithm. I've essentially just created a TSNE object, which has not been fit with any data set yet. And so actually in scikit-learn, we have 2 functions that will perform similar tasks. We have the fit function, and then we have the fit transform function. So the nice thing about the fit transform function is that it actually does 2 things. So the fit part of that function basically runs the algorithm for the supplied data set. And then if you use the fit transform function like we're doing here, it will also fit the algorithm. So basically run the algorithm. And then the transform part of that function will essentially spit out a relevant output for that particular algorithm. So the relevant output for the TSNE algorithm is going to be our 2-dimensional TSNE coordinates for each of the observations in the data set. So we can see that this returns a NumPy array, which is fine. I usually like to deal with everything in pandas data frame. So I'm going to take that resulting set of optimal TSNE coordinates. I'm going to put this into a TSNE plot with these column names. Okay. Someone asking, wouldn't this cause a sample error because you are putting the same data you use to fit it? A sample error. So I think you might be kind of thinking of this in terms of a predictive modeling headspace, perhaps. I mean, so this in sample cause in sample error. So maybe we should discuss after class kind of like what you mean by this here. So this, generally speaking, isn't going to cause any issues here. We're simply just putting in a given data set. And we're not setting this up for like predictive model purposes. So for instance, we're not saying like, let's create this training data set and see how well it performs on a test data set. Because ultimately our goal is not to create predictions for this data set because we don't actually have any predictions, that we're pursuing here. So the train test split method doesn't quite apply if that's sort of what you're getting at, but we can kind of discuss after class that question. And so if I'd like to actually create my TSNE plot, something that I like to do is I like to kind of create this data frame that has all the information that I would want to know about each of my observations. So I horizontally concatenate my original data frame along with my new TSNE coordinates. So axis equals 1 implies we're doing horizontal concatenation. And so for instance, if I want to actually create my TSNE plot, I can simply use the scatter plot function, give it my TSNE coordinates that I've created, and then I can also add this additional element to the scatter plot in which I'm, for instance, choosing to color code by the pre-assigned class labels here. Okay, so this is my first TSNE plot that I found with a perplexity value of 5 and one particular random state that I've used. Okay, so notice this is not the same TSNE plot that I was interpreting at the beginning of the unit. It looks quite different, right? So I can see that there's really not a whole lot of separation. Maybe there's a little bit of separation forming here, but it's very difficult to see, at the very least, looking at this plot alone, any evidence of a clustering structure. So the thing here is just because we do not see a clustering structure in one such TSNE plot does not necessarily mean that one does not exist. So we need that, therefore, we discussed that like the most effective range of perplexity values for gaining the most amount of useful insights are going to be those between 5 and 50. So therefore, it's always a good idea when running or when creating TSNE plots to try out multiple perplexity values across that full range. And then in addition, we also want to try out multiple random states for each of those perplexity values. And you'll see why in a second. But part of the reason why we might not have been able to detect any clustering structure yet is because with a perplexity value of 5, it's possible that we might have been exclusively focusing on the local structure. And because we're not forcing too many observations to be neighbors, to be considered neighbors in the projection yet, it's possible that we may not have been able to detect any of the more global structure or more of the separations that exist. So we're going to go through more perplexity values for this particular data set in just a second. But let's look at a few artificial examples to learn a little bit more about what the TSNE plot can and cannot tell you and how to select the best set of parameters to extract the most useful insights or suggestions from the data set. So what we're going to do here is we're going to actually take an original data set that is also 2 dimensions. So technically, we don't actually even need to be like applying the TSNE algorithm to this data set because we can already see what the clustering structure looks like with our eyes. But the thing here is that, technically the TSNE algorithm doesn't actually even need to reduce the number of dimensions for it. You can take a 2-dimensional data set, that's the original data set, put it into the TSNE algorithm and get a resulting TSNE plot, regardless of how many variables that you have. So let's see what happens when we take this data set here, which has, we can see with our eyes 3 clusters. One of these clusters, it looks like, has a higher sparsity than the other. We can see that these 3 clusters are highly separated. So let's actually see what happens when we run this TSNE algorithm many times. So first, it's always a good idea to start off at the lower bound range for the perplexity value. So I try out 2 perplexity values using 2 random states. Okay, and so we can see here that at least by using a lower perplexity value, for both of the random states, we really did not actually see the existing cluster separation that actually exists in the full data set here. And I'll also take note that the placement of the points are not actually going to be the same across the different random states that we were looking at. So for instance, in this projection here, for instance, like this point ended up being somewhat close to these points here. But then we can see wherever that equivalent point is in this other perplexity or in this other plot, it's actually quite far away from the pink points. Now that's something that we can end up seeing, is that based on the random state that you're using, or in other words, based on the local minimum that the TSNE algorithm is pursuing for that random initialization that you've created, your points, your equivalent points can actually, dramatically change where they are in the projection. Now, what tends to not change as much, or tends to have a higher amount of consistency, is the overall shape of the existing clusters that you may or may not see. So basically, what's happening here is, like, in this projection, we're really only forcing the 5 nearest neighbors of a given point to be close to it in the projection. And so basically the algorithm, given that we know that like this point here and this point here are not neighbors, the algorithm is not really putting as much focus on keeping, let's just say, those 2 points far apart. So basically, therefore, with this lower complexity value, there's nothing really forcing the algorithms to separate the existing clusters that we know exist. So let's see what happens as we move up in perplexity value. So now we're going to try out higher complexity value of 10, and we're going to try it out with also 2 different random states. Okay, and so now what we can see is what we're doing here is we're now forcing the 10 nearest neighbors of a given observation to be close to that point in the existing TSNE projection. And because of that, so basically what we're doing here is we're forcing this observation's 10 nearest neighbors to be close to it. And we're forcing this observation's 10 nearest neighbors to be close to it. So essentially, as we increase that perplexity value, what we end up seeing in the TSNE projections is sort of this chain of nearest neighbors. So it's basically forcing these observations to have to be closer to each other. It's forcing these nearest neighbor chains of observations to be closer to each other. And so basically, in order to do that, we have to the algorithm is going to be focusing more on keeping these observations close and these observations close. And in so doing, basically creating more of a separation that exists between naturally separated clouds of points. But again, we're not really seeing, it's not super obvious yet that perhaps these observations here are distinct clusters. So what we should do is keep going and jump up to higher perplexity values. Again, looking at this for multiple random states. Okay, so here we have, TSNE plots with perplexity value of 20. And I'm going to do the same thing. So going up to 30, looking at plots for perplexity value of 40, all the way up to our pre-specified or our suggested upper bound perplexity range of 50. And so we can see, especially as we go up to these higher perplexity values, we are seeing a lot of agreement in a wide variety of different things or attributes about the resulting clustering structure that we see in the plots. So for instance, if we examine basically across multiple random states or multiple perplexity values, particularly those between 30 and 50, we see the following commonalities about the suggested clustering structure. Okay, so like I mentioned, one of the things that a carefully examined set of TSNE plots can tell you is, for instance, that number one, there is a clustering structure. Okay. Number two, that what this is suggesting about each, or what we're seeing here in each of these 6 plots, is that there are 3 clusters we end up seeing. Also, what we're seeing is that these 3 clusters are roughly spherical in shape. Okay. We're also seeing that these 3 clusters are well separated. And furthermore, we're also seeing these commonalities in which, the same number of observations, or the 3 clusters that we're seeing, roughly look like. They might have the same number of observations in them. Okay, so given that we have seen, in fact, multiple random states and multiple perplexity values across the full range that suggest that there is, in fact, a clustering structure, then what that suggests is that, yeah, there is, in fact, a clustering structure in the original data set, particularly one that exhibits the particular shape, numbers, cluster sizes, and separated nature as the TSNE plots that we're observing. Okay. Alternatively, if we had seen, for instance, across all perplexity values and all random states that we explored, if we weren't able to see any clustering structure forming at all, then what that would suggest is that this data set has no clustering structure. Okay. Now, this is again based on some key assumptions, though, that the TSNE plot is assuming about what makes for a clustering structure, right? So, for instance, if you consider an outlier to be a cluster, or for instance, if you should say you have a cloud, dang it, you have a cloud of points here, and then maybe you have like 5 points here. And let's just say you set your perplexity value be equal to 10. Then your TSNE plots, actually, so let's just say you set your perplexity value to be anything. So this is a cluster, and this is a cluster. Then more likely than not, all of your TSNE plots are going to look like this. Most likely across all random states and perplexity values between 5 and 50. Okay. So, this is kind of this is showcasing that there's no foolproof method that we're going to be introducing to you in this class that will be able to identify all clusters and all clustering structures. And this is just, one such case. So if we have, for instance, a very small cluster of like 5 observations, provided that you're using a perplexity value within this range, this is what all of your plots are going to look like. And therefore, based on that, based on this suggestion that I stated up here, you might be misled into thinking that there isn't a clustering structure when there actually is. So do keep that in mind that, the TSNE plot is never the answer key. There are some things or some elements of the clustering structure that it is and is not able to detect. So take all of this with a grain of salt. Okay. Any questions on that? Okay. Now also take note, something that we saw here is like, so, when we got to a perplexity value of 20, we were for the most part starting to see the formation of the 3 clusters that we know exist. But now take a look at what we saw here. So we actually saw for this particular random state, this larger cluster actually ended up getting split into 2 clusters. And that is in fact something that might in fact happen. So you want to remember, we are solving a optimization problem using a rough heuristic for this optimization problem. So it's possible, a result such as this might have you know, converged or approached, or might have been approaching a bad local minimum. So it's possible, for instance, that the TSNE or the algorithm, using the heuristic that we had, that we used to solve the TSNE optimization problem, it's possible that we might have arrived at a much smaller distance, final distance for this projection as opposed to this projection. But this also showcases why it's important for you to examine not just one random state for a given perplexity value, because it is possible that you will get opposing results. So therefore, part of the art of interpreting your TSNE plots is to collectively take, generally speaking, a aggregate picture of what you are seeing commonly show up across multiple random states and multiple complexities. So given the fact that we see, a strong amount of commonalities in what we're observing here, led us to the best suggestion that there are, in fact, 3 clusters in the data set as opposed to 4. But this is a potential pitfall that you might end up observing, and that perhaps one of your TSNE plots might actually suggest that there are more clusters than actually exist in the data set. Okay, I'm doing a lot of talking here. Any questions on that? All right, cool. Now, let's think about, so we talked about some aspects of the original data set clustering structure that we are able to see preserved if we've selected the right parameters for a given data set. So, the number of clusters, the shapes, whether they're well separated, how many observations are in each of the clusters. But simply just based on what we've seen here, comparing our original data set to what we see in our TSNE plot projections, what are some aspects of this original data set's clustering structure that was not preserved in the TSNE plot projections? So what are some differences that we're seeing here between like this and this? We can definitely see this does not look exactly like this. So what's different? Yeah, exactly. Yeah, okay. So the key thing that you want to remember when it comes to interpreting your TSNE plots is, oops, you want to remember that TSNE plots do not preserve the pairwise distances between the observations in the original data set. Okay. So for instance, we do see here that like this point here and this point here, we're about, this distance away. And, this point here and this point here, we're about, this distance away. But what we can see here, for instance, is that this point is perhaps about this distance away in the TSNE projection, whereas this point is, a much larger distance away. So we can see here that this is an example in which the 2 pairwise distances between these 2 sets of points were not proportional, or they were not essentially preserved in the projection. So because we cannot trust the pairwise distances between any given pair of points in the projection to be preserved, what that means is other aspects of the clustering structure that cannot be preserved are things like the sparsity of the clusters cannot be preserved in the projection. And furthermore, also follows that thus the distance between clusters in the projection is also not preserved And then furthermore, something that we're also seeing here is that the location of the points in the projection are also not proportional or preserved. Compared to the original points in the original data set. Okay, so we're going to see that this lack of pairwise distance preservation between points is also going to lead to other aspects of the original data set that are not going to be preserved. And we'll explore that in just a second. But any questions on that? Okay, now one key point that I also wanted to focus on here is essentially what we saw in this scenario is that we were able to identify the clustering structure from the original data set as we focused on higher perplexity values. But that's not always necessarily going to be the case. So one of your homework assignments is going to focus on a scenario such as this, in which there are some data sets in which you will only be able to see the clustering structure of the original data set when you're specifically looking at lower perplexity values. So I don't want you to think that, just by increasing the perplexity value, you're more likely to detect the clustering structure. So it very much depends on the nature of the data set that you're looking at. So this is why it's always a good idea to look at the full range of perplexity values between 5 and 50. Okay? All right, so let's look at another. So basically, these are just kind of outlining some tips for how you would go about using the TSNE plots to infer what the clustering structure of your original data set might look like. So this, again, just kind of review some of these here. But the key thing here that you want to remember that I haven't mentioned yet is that, again, the TSNE algorithm is not a clustering algorithm in and of itself. It is a dimensionality reduction algorithm that basically can be a useful aid when it comes to, double checking or corroborating the results of an actual clustering algorithm like k-means. And the reason why is, again, because the TSNE algorithm skews or does not faithfully represent the pairwise distances between pairs of points. So for instance, you might decide to take this TSNE plot projection and throw this into a clustering algorithm. So the first thing is, technically you don't even really need to do that because you can kind of see this with your eyes, if you will, what the suggested clusters are. But another issue is that some clustering algorithms actually, many of them do actually rely on, having a faithful representation of each pairwise distance that exists between pairs of points. So therefore, by clustering a data set such as this, you're sort of warping the pairwise distances from the original existing data set. And this can lead to very misleading clustering results based on sort of just the random placements that 2 points might have been for a particular random state. So for instance, one clustering algorithm may have put these 2 points together if you'd been using one particular random state TSNE plot. But if you use a different TSNE plot, you might have gotten a different result when putting that into a clustering algorithm. The bullet point is, don't think of this as a clustering algorithm itself, but more of just an aid. All right. Okay. All right, so let's take a look at another example. So here, there's another original data set that we used to create these 12 TSNE plots that I'm showing here. And again, we're going through the full range of perplexity values, so 5. And for each of these perplexity values, I'm using 2 random states. Now, it's actually it's technically a better idea for a more complete analysis to try out more than 2 random states for each perplexity value, because you might see more fluctuations based across more random states. But for learning purposes, we just focus on 2 here. And now let's try to think about, based on what we're seeing here, would our interpretations suggest that this data set does have a clustering structure or not. So technically, I give the answer about what this original data set looks like in the next page, but let's focus on what we would actually just interpret based on what we've seen here in these plots. So I'll open up a poll. Do we think, or would our interpretations suggest that the original data set that created these plots is clusterable? So yes or no? Okay. All right, cool. So I like that I'm seeing some disagreement here because, in fact, based on simply these plots alone, there could actually be multiple sensible interpretations that you could have made about the clusterability of this data set. So here's the thing. It's entirely possible, actually, that you have this data set that is comprised of very small separated clusters. So maybe your original data set did in fact have a bunch of small clusters that were about that contained about 5 to 6 observations within them. And so if that is in fact what your data set looks like, then this most likely would be what your TS&E plot with 5 complexity value of 5 would look like. On the other hand, though, yeah, and so basically, and if that was the case, as you increased that perplexity value, unfortunately, what the algorithm would do is it would essentially force a lot of those little mini clusters to get pushed closer and closer together, such that you were unable to really see the separation of those points. Now, here's the thing that you want to keep in mind is that, when you're dealing with larger, I'll just say convex clusters in particular, this is often what you will see when looking at a low perplexity value like 5. So this creates this additional layer of confusion. So based on what we see here, it is possible that your data set does have, very small separated clusters. Or these mini clusters may only be appearing because the algorithm is focusing on just the 5 nearest neighbors and not being forced to focus as much on the global clustering structure. What I'm saying here is technically, this could in fact be the case. Now, quite often, a lot of our data sets do not have this many clusters, but it is possible. So let's see what happens if we increase this perplexity value. Okay, so basically, as we're increasing this perplexity value, we see not a whole lot of separation, but there is a little bit of this gap showcasing itself in many of these blobs of points that we end up seeing here. So based on that, I would be a little bit unsure as to what actually is being represented or what actually the original data set looks like. So what I'm seeing here is because there are multiple TS&E plots across multiple random states, and perplexity values that show this cloud of points with slight gaps on the edges. This could also lead to two other interpretations. So it could be the case that this gap, these two gaps that we're seeing here, is simply just a fluke. So you might actually, based on how you're really examining the edges of this cloud of points, you might interpret this as saying, yeah, like I only see one, distinct cloud of points here. So you might just say, there is just one distinct cloud of points. Thus, this data set, thus this might suggest that the original data set is not clusterable, or in other words, it simply just has one cluster. On the other hand, we may in fact interpret these two sets of points that exist between, kind of these gaps here as perhaps two clusters that happen to be not well separated. Or we could interpret this as showing two sets of points that are not well separated. So this might also suggest that the original data set has two non-well separated clusters. Okay, so this is some of the ambiguity that we can essentially get even when we're being the most careful and examining multiple perplexity values and multiple random states across the full range. So it could be, in fact, simply just based on what we're seeing here, it could actually be any one of these three interpretations that we have come up with. And then on top of that, like we mentioned, it could actually, there could actually be some additional clustering structure that we're not detecting. So, maybe there was, in fact, this small little group of, points that counted as its own cluster in the original data set. But, the TSNE algorithm had to force it to be close to, a higher number of neighbors, if you will. So, therefore obfuscating the clustering structure. So again, it's possible that even these three interpretations may not actually be telling the full story about what's going on with the original data set. So this is, in fact, what the original data set looks like. So, based on whether or not you think that this data set is clusterable may, in fact, actually explain these two interpretations that we got here. So now I'll tell you right now, I randomly generated this set of points from a two-dimensional Gaussian curve, or Gaussian PDF. So it just so happens that this particular random set of points did in fact happen to have this slight gapping that exists in the data set. So whether or not you choose to say that this is in fact a non-clusterable data set or a set of two clusters that are not as well separated, that's kind of based on your own interpretation. Okay, this kind of showcases how the general structure for how you might effectively try to make the best suggestions about what's going on. But then it also kind of showcases some of the pitfalls that you might experience when making these interpretations. So I'm seeing a question here as, does the ambiguous TSNE plot mean or necessitate that the base data set is also ambiguously clusterable? Low separation outliers points. Are there cases when unambiguous clusters that have ambiguous TSNE plots or vice versa? Yeah, so for instance, we saw a situation like this where, these three sets of points are, I would say, unambiguous. There's unambiguous, three clusters here. But for instance, we saw this TSNE plot projection here that split one of those clusters in half. So that, for instance, would be a scenario in which, you have this very unambiguous set of clusters, but your results are ambiguous, if you will. I think that answered the second question. Does an ambiguous TSNE, yeah. And so we're going to look at another scenario in which there is a ambiguous, TS&E plot that that maps onto also an okay. So I think I answered that question. Okay. So let's look at another example just for practice. So let's take a look at this data set here. So this is my original data set. What I can see actually, the way that I generated this data set is we have four highly overlapping Gaussian data sets that I've generated here. So we can interpret this, for instance, as four overlapping or non-well separated clusters in the original data set. And so let's take a look at what my 12 corresponding TS&E plots show. Okay, and then the question is, it's kind of hard to see, do we think that our TS&E plots were able to detect this weak clustering structure, as well as the shape and the size of each cluster? Let's see what we would have interpreted. Okay, so based on the interpretation methodology that I've been showcasing to you so far, do we think that we would have been able to suggest the fact that there are, in fact, four non-well separated spherical clusters here? Okay, yeah. So we're saying yes for the most part. Yeah, based on I'll say the fallible, so the imperfect rule of thumb that I've been, showcasing about how to interpret these plots, we would have been able to identify some key elements of this clustering structure here from the original data set. So we can say, because there are multiple perplexity values and across multiple random states, that showcase four well-separated spherical clusters that are roughly balanced in size. Our interpretation rule of thumb would have correctly suggested in this case that this, in fact, is what is going on in the original data set. Okay, but do take note, right? We do see one particular random state in which the original data set clustering structure is not as perfectly represented. So for instance, we do see that two of these sets of observations had a perfect separation. So that's why it's always important to get a aggregate sense as to what multiple perplexity values and what multiple random states are telling you. Because simply just by looking at this one might have misled us about the structure of the original data set. So it's possible, for instance, this TS&E plot here might have gotten caught in a bad local minimum. Okay. Any questions on that? Okay. All right, so let's take a look at another example. So here we have this data set here. We have two main clusters that we definitely want to count as clusters. And then we have a few outliers in this data set. So let's take a look at what the TS&E plot does as we look at multiple complexity values and multiple random states. Okay, so what you want to remember, and we've been discussing this already, because the TSNE plot forces an observation to be closest or to be close to its nearest neighbors, whatever nearest neighbor or the perplexity value nearest neighbors, then usually what that means is that outliers end up getting forced into larger sets of clusters. So we don't actually see usually the existence of outliers in the original data set. And so that is in fact what we end up seeing here. So basically these points end up getting forced to be close to their 5 nearest neighbors, for instance, when stipulating the perplexity value is 5. Okay. Now, something interesting that happens here, right, is that, well, okay, actually, in this TSNE plot projection, actually 2 of our outliers actually did remain as outliers. But then, whoa, okay, what's going on here? Okay, so this kind of showcases that you need to be really careful when it comes to interpreting outliers based on what a TSNE plot is telling you. So basically, the bullet point is the TSNE plot should not be giving you any indication one way or another if there is or is not outliers in the data set. So what you want to remember is if you don't see outliers in a TSNE plot, then that does not mean that there are no outliers that exist in the original data set. Okay, that'd be something like this. So if you said, based on what I see here, there are no suggestions of any outliers, that would potentially be wrong. On the other hand, you might have a scenario such as this, right? And so basically, another key thing to keep in mind is if you do see outliers in a TSNE plot, then that does not necessarily mean that they are outliers in the original data set. Okay, so bullet point is, when it comes to TSNE plots, don't use it to really say one thing. Don't really use it to say anything about outliers. You should use other techniques that we're going to discuss in this class. Okay. All right. Questions on that? Okay. So again, this is kind of going through the exercise of how our rule of thumb interpretation, what it might end up telling us, about a data set. So based on our rule of thumb, and these, the aggregate of all of the TSNE plots that we're seeing here, what I might say, the rule of thumb interpretation might say something like, 1, this data set is clusterable. It has 2 roughly spherical clusters that are well separated and roughly balanced in size. Okay, saying nothing about the outliers. Okay, so one more example that I'd like to look at here is showcasing some pitfalls that we might have, that we might encounter when the data set that we plug into our TSNE algorithm has noise. Okay, so we see here that this is our original data set. Okay, and these are the set of TSNE projections that we get. Again, looking across multiple random states for our full range of viable perplexity values. Okay. Now, unfortunately, if I were to use my rule of thumb interpretation, what I'm seeing here is I would actually end up making some wrong interpretations about what the original data set actually has going on. So what I might say, for instance, is, okay, given that I'm seeing actually about at least 7 clusters, showcasing themselves across multiple perplexity values and multiple random states, that might be my misinterpretation. So I say, given that I see the following across multiple complexity values and multiple random states, particularly those perplexity values that are between 30 and 50, I might, in this case, incorrectly suggest the following about the original data set. So I might say there are 7 clusters in the data set. So that's wrong. Say at least 7. 4 of those clusters are roughly spherical. So that's about right. And then the 3 or however many remaining clusters are showing some sort of a non-convex, sort of oblong pattern, if you will. So definitely not spherical. So 3 or more of those remaining clusters are oblong, not spherical, or even maybe non-convex. Okay, and it might suggest that these clusters are well separated. Which is for the most part true. Okay. And it might also give us an indication as to how many observations exist in each of these clusters. So some of these things are right, some of these things are wrong, but it does showcase a potential pitfall that you might experience when examining TSNE plots for data sets that have noise. Okay. All right. So okay, I need to get through some stuff really quickly here. So just to recap, here are some things that the TSNE algorithm and the resulting TSNE plots can and cannot tell you about the original data set. So 1, it can, in fact, suggest, and again, the thing here is none of these suggestions are foolproof, but at the very least, it has the capability of suggesting this particular aspect. So I'll say this here. So none of these suggestions are foolproof, but it's possible for you to make that interpretation sensibly. So it can suggest if or if not a clustering structure exists. It can suggest the cluster shapes. It can suggest the appropriate or the number of inherent clusters that exist in the data set. It can suggest the approximate number of observations in each of those clusters. It can approximate whether or not those clusters are, well separated. Now here's some things that it cannot suggest, okay? So again, key thing that you want to remember, pairwise distances between points in the data set are not preserved in TSNE plots ever. So it's kind of foolish to try to make that interpretation. You're never going to get it right, basically. So no, it doesn't suggest that. And thus, because of that, it's not a good idea to interpret the distance that exists between clusters in the TSNE plots. For similar reasons, you should not interpret where the centroid of a given cluster is. So for instance, just because a point is centrally located within this TSNE plot suggested cluster does not necessarily mean that it is the centroid of the original dataset cluster. Okay. Similarly, you cannot determine sparsity of the clusters. So for instance, just because these clusters have the same sparsity, or so it looks like, does not necessarily mean that the clusters in the original data set all have the same sparsity. Okay. And then finally, you cannot detect the existence of noise or outliers based on what you see in a TSNE plot. Okay, it's a little bit rushed, but any questions on that? Okay, very quickly, this will be the last thing. So let's go back to the application where we're applying the TSNE plot on our shill bidding data set. And so basically we're going to do what we just did for each of our artificial examples. So we're going to examine multiple perplexity values and multiple random states. Okay. And we're going to use the code that we used above, basically, to create the corresponding perplexity values and or the corresponding TSNE plots for each of these perplexity values and random states. Okay. Basically, we're seeing with the low perplexity values, we're not really seeing the existence of any strong clustering structure yet. Okay. However, as we continue to increase in that perplexity value, we are in fact seeing the formation of 4 distinct clouds of points in the data set. And for the most part, they are also showcasing the same general shape. Okay. So based on the fact that we've seen the same set of patterns across random states and multiple perplexity values, what this suggests is what we described at the beginning of the unit. Okay, that there are, A, this is a clusterable data set. B, there's 4 clusters. C, that these 4 clusters are in fact well separated. And D, these some of these clusters might be roughly spherical. Perhaps some of them are non-convex, essentially. Okay. And so just one final thing. So I might decide to cluster the data set using k-means. So that creates an additional set of labels for my data frame. And so, for instance, I might, again, and this is what I did at the beginning of the unit, I might decide to color code a carefully selected TSNE plot. So basically one that best reflects what I suggested upon observing multiple, multiple patterns of this in multiple random states, multiple perplexity values. And what I see here is that my 4 k-means cluster labels, in fact, have a very strong alignment with the 4 TSNE plot suggested clusters here. So basically what this does is this provides an additional layer of corroboration that the 4 k-means cluster labels are in fact meaningful. Or in other words, they are identifying 4 well-separated sets of points, which is good. Whew, okay. All right, so that's basically it. So that is enough to do the next homework assignment that I'm going to be posting. All right, so I went a little bit over. So thanks for sticking around. I will stop